Welcome to Philoctetes Center. Francis Livy and I are co-directors of the center. Today we have the last of the series which began a few weeks ago, and we started with the nature of reality, then we had limitations of explanations, and today's theory of everything. And it is a theory that is supposed to, which I don't think really exists yet, but which is supposed to explain everything. And somebody asked me a couple of days ago, would it explain Cain and Abel? And I said, I'll ask today and see if the participants can deal with that issue. So I will introduce, as we usually do, Professor David Albert, who will be moderating, and then he will take charge of the rest of the meeting. He's professor of philosophy at Columbia University. His research is primarily on the foundations of quantum mechanics and the nature of time. He has published numerous articles and 2 books, one called Quantum Mechanics, the other Experience and Time and Chance.
Actually,
it's one book?
Mechanics and Experience is one book.
Oh, Quantum Mechanics and Experience, Time and Chance is the other? Okay. And now he's working on a new book called After Physics. Professor Albert.
So let me just welcome my fellow panelists and maybe ask them to just say a few words about themselves and their work. First, Glynis Farrar.
So I started off as a particle theorist and did particle theory for many years. So maybe that's, I'm not really sure, unless they were looking for a skeptic, how I happen to be on the panel. But I'm really more of a phenomenologist, which means a person who is really interested in trying to understand and explain what's going on in nature. Maybe ask questions, can you test a certain theory and that kind of thing. But somewhere in between theory and observation, or theory and experiment. And then in recent years, I've more and more been using cosmology and astrophysics as a test bed for new physics. I'm very interested in the possibility that there's more to nature than what we see in what's called the standard model, and trying to find ways to get at that. But of recent years, I'm doing mostly, in practice, 90% of my work is in astrophysics and cosmology, and a little bit of what's called astroparticle physics, which has to do with ultra-high energy particles that get to you from the other side of the universe, that kind of thing.
Charles,
very practical.
Hi, I'm Charles Liu, and I'm even more practical than Glynis. So I am 100% an astronomical person. I do astronomy. I'm an observational cosmologist. I study the evolution, the aging of galaxies and of the universe, the star formation history of the universe. So my side of science is to present and gather information about the universe, then provide it to great thinkers like Glynis and my other colleagues here to help us explain what those things actually fit. And if it's one thing that we observational, experimental people have found out about the universe in the past century or more, is that the cosmos has a way of making theories of everything seem somewhat inadequate. And so I always hope that a true theory of everything will eventually be successful in explaining everything. But until then, I live in the world of what we see, what we touch, and perhaps that's not necessarily a good thing, but it's probably not necessarily a bad thing either.
Thank you. Herman Verlinde.
Okay, so on the scale of practical and unpractical, probably I'm in the unpractical side of the spectrum. How do I end up on this panel? Maybe I should go back to a time when I was growing up. And for me, there's a clear memory of watching a television program about things that I had never heard about before, about how the world consists of particles that have funny colors and that are interacting with each other. We call them now quarks. I'd never heard of those things before. And then there was in the same program, the scientists were explaining how they were uncovering the rules of things smaller than we can see, but also things bigger than we can imagine. The cosmos, black holes. Hawking was in that program explaining how black holes perhaps actually are not black, that stuff can actually escape from a black hole. I thought, at that moment, a whole world opened for me. I was maybe 13, 14 years old. At that point, I thought, well, I want to know more about what's behind all this. And that sort of started the road and brings me here. Later, I started working. Maybe I wasn't sure what direction I would take, but when I was choosing my topic for my PhD thesis, that's indeed when string theory got started as an exciting new idea of how to combine precisely these questions of how the smallest things might fit with the largest things. And it was such an exciting sort of atmosphere at the time. It sort of enhanced this feeling that I already had, that I wanted to know more about it. So that's how I ended up being a string theorist. And I moved to the United States 20 years ago in Princeton. I've been there most of the time since. Although I would call myself a physicist, being motivated by really what's out there, because that's really what creates the fascination, the fact that you can explain things that you see, which is a magic fact. I do a lot of mathematics as well, but today we talk about maybe the application of that mathematics to reality. So we'll see where that ends up.
Thanks. And Garth Williams.
Well, after such expertise, you'd be disappointed to know that I'm a professor of classics at Columbia. And I feel rather out of my depth in certain obvious respects here. And a further disadvantage is that when I came in this afternoon, I then saw Philip Mitsis, a very prominent ancient philosopher from NYU. So I feel great about life. As a classicist, I am very interested in the literature of the Roman period in particular, and I have drifted into a great interest in literary depictions of scientific endeavor in antiquity and literary responses to natural phenomena such as earthquakes, tsunami, etc. we all bear in mind yesterday. And so in that respect, I am very interested in the reception point of physical ideas, how they are depicted, thought about by essentially artistic writers.
Great. Thank you, everyone. I guess my job here is to throw out a couple of hopefully provocative questions that'll get people talking. Maybe we can start by talking a little bit about exactly what it would mean, exactly what it would amount to have a theory of everything. And let me focus first on one particular aspect of that. Almost all contemporary discussions of a theory of everything seem to equate a theory of everything with a completed fundamental physics, with a complete theory, that is, of the behaviors of the fundamental physical constituents of the world, elementary particles or fields or strings, or what have you. I'd like to hear a little bit from the panelists, first of all, just about that. Is a complete account of the fundamental laws of physics transparently, in fact, a theory of everything? Is there some principled sense in which physics is all there is? And I'd also be interested in views of the ancients about that. But if anybody has
Can we ask you?
to say.
Since
You want to ask me?
Since you're writing the book called After Physics, perhaps you're exactly the right person to start off that question.
Let's put it this way. I don't want to impose my views here. There are lots of people. Everybody is familiar with worries, for example, about the extent to which things like mentality can even potentially be reduced to physics. And within philosophy of science, there are much more specific worries about whether many of what we call the special sciences. There are lots of people around who say they have a hard time imagining how sociology or economics or psychology or even biology could be in some satisfying way reduced to physics in the sense that it could be demonstrated clearly that whatever we think of as the laws of economics or the laws of psychology or the laws of biology are in fact, at the end of the day, nothing but Schrodinger's equation or nothing but this or that Lagrangian or something like that. So I wonder if people around this panel have
Do you
opinions
have a problem
about
with the idea that biology is underlined by chemistry?
I don't have. I mean, if the question is about my opinion, maybe we're all going to here disappointingly agree with each other too much. So let me speak. Let me speak first for people other than myself. There are plenty of people around who say things like this. First of all, I don't know what. Words that are significant, say, in economics. Contract, exchange, payment, blah, blah, blah. None of these terms are terms which have clear and explicit translations into vectors in a Hilbert space or something like that. There are a lot of people who worry that although one can hand-wavingly say, look, these are all physical events and so on and so forth, they're not carved up into categories in anything remotely like the way we carve things up into categories when we're doing fundamental physics. That's one kind of worry. You might call it a worry about translation of special science terms into the terms of fundamental physics. There's another kind of worry that has to do with explanation. Okay? That whereas somebody might say, I have no doubts that in the case of any particular perfectly clearly described physical event, we can go back to the physical initial conditions of the universe, plug in the laws, we'll have a successful explanation of that event. But there are all sorts of things of a much vaguer and more general sort that we're used to saying in economics, that we're used to saying in biology, that we're used to saying in psychology, so on and so forth, which, so these people will say, have a kind of explanatory significance that can't be reduced by simply tracing the microphysics of one or another of these events. So those are two kinds of worries that people raise. Now, it may be the sorry upshot of this that nobody here has much sympathy for those worries, and as a matter of fact, I don't either. So that'll make the conversation less interesting. But if you want me to pretend that I do for the sake of the conversation, I can do that. Yeah, you wanted to say something.
Yeah. Of course, this has to do with complexity. At least
right.
Once you get started with simple principles, and there are these famous examples that very simple principles can sometimes give rise, once you look at it at larger scales, emerge to new order and new structures that lead to very complex behavior, and eventually you can even imagine that could lead to the type of complexity that you see in cells or etc. Personally, although I'm kind of indeed driven to try to answer these questions that are sort of more what we call on the fundamental end, where maybe the actual laws by which things start at the smallest scale or maybe even at the largest scale have a mathematical description. That's what drives my curiosity. I don't think I'm too idealistic when it comes to actually expecting that we'll eventually have an explanation of all these more complex situations, like what makes us, what is consciousness, or what drives a society. Those are things that clearly physics has nothing really to say about, and indeed one has to use different starting points as a way of describing it. So I'm very pragmatic when it comes to that point of view, to those kind of questions. I guess if you talk about the more philosophical sort of question of whether there exists such a thing as,
Right.
as an underlying explanation of everything, then you would have to ask, well, is it possible that there could be two worlds with exactly the same periodic system and exactly the same Schrödinger equation, but it leads to completely different biology because there's a sort of a level of complexity in between there where a new fundamental principle has to be added in that somehow is not defined from the microphysics.
Presumably all of us think that there could be two worlds for each of which, say, the Schrödinger equation is the fundamental law of physics,
That's right.
which give rise to different biologies.
Correct.
Presumably, most of us think that even within this world, there might be different biologies in different galaxies or different planets.
That's right.
So surely the answer to that is yes.
Yes, there are at least the organizing principles at a higher scale may be different, and life may decide to do something different.
All sorts of things about biology could easily be imagined to depend on whether at a certain very initial point something turned right or turned left. And then you had left-handed molecules, being the foundation of biological systems. And all sorts of things could be different.
Right.
So presumably nobody is of the opinion that, say, once you've written down F equals ma, or once you've written down the Schrödinger equation, you've made it clear exactly what kind of biological systems you're going to find in the world.
Yeah. But Weinberg in his book he introduces this notion of the arrows of explanation, which sort of comes back to the same kind of question: is that can we imagine that arrows of explanation go from more complex systems to more simple systems, and that. We haven't really done that.
And that seems more in the nature of the question. And as to something else you said, presumably, nobody is going to recommend reduction to physics as a good methodological strategy. Nobody is going to recommend that, say, the way to conduct psychotherapy is to first write down the Schrödinger equation of the guy's head, and so on. Surely the questions at stake are just of a more principled kind. Is there some principled sense in which, if you had a computer whose computational power and speed were unlimited and so on and so forth, and it was fed the laws of physics, it would also be able to explain why Obama won the election and so on and so forth?
Yeah, that's a bit of a jump there, but okay.
But how can you even, this is maybe a problem I have with philosophy. I guess I wonder what's the point of having some abstract discussion and opining about that when don't we just have to try and see how far we get on explaining different things from, one level? And I would suppose, but it's really a religious question, that once the physics is understood, that everything else in principle would follow. But it may not be so, but how would you know just by thinking about it?
It's the principle that's the stumbling block there. Like he was saying, nobody suspects that physics is ever going to get to the point where we're able to write down a Lagrangian for the universe, and then some computer or some human being is going to be able to extract from that interesting economic data or something like that. Nobody suspects that. So that's not something that we're likely to decide upon by seeing how far our actual calculations in physics get us. But we might be interested nonetheless in a question of the form: is there, in some principled sense, anything else to the way the world runs besides the fundamental laws of physics?
Well, science is relatively young. My thought is that basically philosophy's been around much, much longer than the scientific method of getting information. Right? Science today could be considered some small portion of the natural philosophy that was studied in the ancient times, including, say, Aristotle and those forth. So a theory of everything maybe 400 years ago was probably a lot more elegant and beautiful than it is today, based on our attempt to understand physics or biology or chemistry, and realizing that, for example, in this room there are more air molecules than there are stars in the entire observable universe. Surely that must require some way of thinking beyond just pure particles to explain bulk properties. But it doesn't negate the fact that bulk properties are defined on the microscale by individual physics of individual particles. Okay, the Aeneid. Is there a theory of everything in the Aeneid which predates the Francis Bacon's scientific method by 1,500, 1,600 years? That would be interesting to me, at least in the context of this conversation.
You're mentioning the ancient. For me, the Greek were always I had fascinated by them, because in those times they started realizing that things could be explained, that there are regularities out there.
Yeah.
And to me, in some sense, we could even go back to that. Okay, do we really believe that the hints that we have that things behave the same way every time you look at them, at least in a certain way? Because, by the way, if you talk about the theory of everything, a bit more than 100 years ago, or at least 100 years ago, still people might have believed that it would mean, a theory of everything would mean that if you you say what this cup looks like at a given moment, and you build a big enough computer, then you would be able to say what happens a little bit later to it by just calculating the laws of physics for it. And we already know that that's not the case. You can have two elementary particles, and they look exactly the same, but one of them will start doing something completely different than the other one, on the basis of something that we don't know what it is, because that's what quantum mechanics tells us, that things cannot be predetermined. So in that respect, we have already made an enormous concession in what we mean by a theory, a physical theory. Basically, it's no longer a theory that will predict what will happen, so there's something missing about what we do. So what we mean by a theory of everything, it's an empirical theory that tells you that if you do something sufficiently many times, then with a certain statistic, if you average over it, then we can tell you what the ensemble of outcomes is.
So maybe it's worth being a little bit more precise about that. So
that's a big concession.
Once upon a time, what we hoped we meant by a theory of everything was that was encapsulated in the hope that by giving initial conditions, by giving some complete account of the physical conditions of the world at a certain time, and then plugging them into the laws of nature, we could get out of those laws the complete trajectory of the universe. Now we mean something a little different. Just trying to follow up on what you were saying, we mean something like, given a specification of conditions at some particular time or over some particular space like hypersurface or something like that, what we expect from the laws is a probability distribution over possible physical conditions of the world at all other times.
I would have thought that most physicists, when asked, is there a theory of everything, wouldn't have meant that precisely. And I think there's sort of two. Hermann is really the one that will be the authority on this, but I'll go ahead. So it was certainly the case when I was in graduate school and for many years that it was what people's goal was to simply describe accurately the laws of nature, and that would include what particles existed. And so if you could list all of the different particles that could be created, and you had formulae that would describe the process. It didn't bother people by then that it was probabilistic because of quantum mechanics, because quantum mechanics is just one of the laws. So the fact that it wasn't deterministic just really wasn't an issue. But in any event, so at the time of the Standard Model was discovered, people really were quite content with simply getting the right description, and that felt like discovering the theory of everything. But now it's really quite different because of string theory, I think. And one would maybe go further and say,
how would you formulate the difference between back then and right now?
well, I think now it's not. Well, I think now, practically speaking, theorists actually believe they might arrive not just at the description, but some sort of a demonstration about the uniqueness of the description. So I remember Ed Witten, there was a period when he really thought that there was going to be one possible mathematically consistent theory, period. Which was
one logically possible.
Yeah.
Well, you're just trying to distinguish mathematically and logically?
Oh, no, well, I just wanted to make sure.
Because I said mathematically.
Right.
Okay.
But I mean, that...
So let me finish. So I think that there was a time which was a huge change in people's outlook when people quit just trying to describe it. Because what happened is that the standard model is so complicated with 147 parameters or something like that, if you count all the different particles, and it's not that many, but in any event, when you count all the different particles and all the different interactions and so on, it's very complicated. And it doesn't seem to be particularly natural. Why should there be 3 families, and why do they have those masses that are such crazy relations to each other? So people wanted to try to find some underlying principle, some simpler theory out of which it would all emerge. And I think there really was a period when a lot of very, very smart people really thought that it was going to turn out soon, that they would just discover this one perfect theory. And what's happened is this very huge transformation in people's perceptions in the last maybe 10 years.
You're right.
This thing called the landscape, which maybe a lot of people know about, which is the fact that string theory seems to have something like, I lose track, 10 to the 10 to the 500, some very large number, you'll correct me, of different possible equally good theories. And so from that perspective, you wouldn't expect to be able, but then string theory would still be the theory of everything, and yet you'd be left not being able to predict, because it would be a matter of chance which universe we wound up in, and the universes could flip in between each other and tunnel into another, and new universes would come out, and so on. And so you would completely, even though you had discovered in principle perhaps the true theory of everything, you couldn't calculate anything. It would be kind of an ironic situation.
But let's go back. Well, let's go back to the situation you were describing 10 years ago. Is it really the case that anybody suspected, even for a minute, that that there was a single account, that at the end of the day there would turn out to be a single mathematically possible account of the way the world is, in the sense that any other account would have violated some principle of mathematics?
Let me
because that seems hard to... That is, what principle of mathematics would it violate for everything to be golf balls? Or for there to be nothing? Or something like that?
Let me say a few things about it. I don't think it was widely necessarily believed in those days that there would be this particular unique description. Especially, I think it was maybe hoped. And actually, when I was a student at the time, and I wasn't convinced of that at all. So I think most people had sort of had doubt. But I do want to mention one thing which probably would explain this. Because this was less than 10 years after QCD was discovered and the standard model was put in place. And if you think about what QCD accomplished, it's a pretty amazing thing, right? There's nuclear physics, which is one of the most complicated things that puzzles that physicists had to crack, because there's so many phenomena. And then in the end, it turned out there's one simple Lagrangian, as was mentioned, there's QCD, quantum chromodynamics, and you can write it down in one line, and then indeed you build the computers, and people have done that, and they can get all these numbers out. And if you've achieved something like that, such a huge simplification of what happens at the micro scale, and actually it's pretty important experimentally what the predictions came out, so it's real reality that you're describing. So you've had that accomplishment 10 years ago. The reason why I didn't believe Witten's prediction, because in those days, for me, 10 years seemed like a long time ago. And I had moved past. But now I know that 10 years ago is not that long ago. And you probably still are on a high of having made that discovery.
Yeah.
So people like David Gross and et cetera, who have been making these statements, were obviously extrapolating from that experience. And I think that in that respect, I think there was a part of them that believed that this new simplification, that the same kind of simplification that they found earlier.
I have to. Now you've caused me. I have to modify the theory. People imagine had to have certain, let's say, physically reasonableness characteristics. So they had to be what's called causal. Things, for instance, wouldn't happen before their cause, and it needed to be unitary, which just means that the total probability that something happens is 1. And I'm forgetting the third one. Anyway, not even locality, but in any event, there's some very basic general principles, and that there really was this possibility that string theory, which seemed, and it had to have gravity and a few properties that we already knew. But the thing that is amazing is that if that actually were true, I think in principle, as I understand it, I've been wanting to get to ask you this, it really could be the case that in sort of different big bangs, you'd wind up with universes with different numbers of dimensions, that it would turn out that there, in some sense, there isn't space. I mean, we think of space as being so fundamental, the space that the rest of the stuff is in. But I think that there really is a possibility that in string theory, that is actually just emerges.
Right. Now, so coming back to a remark was made also earlier, the fact that
you have to answer me. Is it true that string theory?
I'll
you're working up to that.
I'll work to this to an answer. I will not say yes or no. It was mentioned about all the gas molecules in this room, and no one would want to take a task of describing where every gas molecule is. So, and nonetheless, we have a pretty good way of understanding what happens here. So actually, in the discussion between the two of you sort of jumped away from the uncertainty that quantum mechanics introduces to essentially applying that uncertainty to the search of a theory of everything. So maybe the theory of everything is a little bit like all the gas molecules in this room, in that you shouldn't be trying to sort of pinpoint exactly where all the gas molecules are. Maybe you should actually take a much more pragmatic approach of what you actually really call the theory of everything. So, and just to mention a few things. So thermodynamics was developed by Maxwell, Gibbs, and Boltzmann, and at a time where the exact structure of the periodic table was not completely known yet. Nonetheless, they had ways of deriving the laws of thermodynamics that are applicable. And even if they would have lived in a universe with a slightly different periodic table, their laws would still have been valid. And one of the things that we've been learning over the last 20 years is that in some ways the laws of gravity are quite similar, in the sense that you could imagine that there would indeed be other worlds with different periodic tables, different electron masses or whatever, but the laws of gravity would be the same. The laws of hydrodynamics would be the same. The laws of economics probably would be the same. So in some ways, the laws of economics are more fundamental than the fundamental laws of physics, because they apply to more than one single precisely determined system. And it could be that indeed the details that we've been able to uncover about the microphysics, about exactly what we call the standard model, indeed some of those numbers, to me indeed the electron mass is maybe less fundamental than the fact that there's gravity. Yeah, it's a much more fundamental fact that things fall down with the same speed, at least. And it is more fundamental in the sense that if we would imagine another universe, gravity would probably look exactly the same.
Could I interject something else? We have a classicist here, and I'm just wondering that in ancient time, that what you seem to be saying is that empirical data in and of itself is not the necessary presupposition for developing perhaps perceptions or ideas about the nature of reality. Right. And hence we have Lucretius, right, on the nature of things, on the Rerum Natura. Were the ancients bolder or equally bold in coming up with theories of everything? And is this a kind of striving in mankind that perhaps, well, yeah, I mean, I'm just picking up from your point here now.
Well, I get free tuition by sitting here listening to the experts.
As do we, sir.
The first question I would have is, and I'm not going to try to describe the one-shot explanations of, being that come from Plato or Aristotle. The question I would have is, what is the impulse to seek a theory of everything?
Yeah.
Now, of course, I understand that in the modern world, the per se experimentation and joy of discovery must be astonishing, and the progress in the last 10 years, the motivations must be quintessentially per se. But for the ancients, I would suggest that it is a very pressing concern to ask, what is the impulse and motivation to seek a theory of everything? And I would suggest that while there were doubtless ancient discoverers, there were who were interested in per se theorizing about the nature of the world. The nature of that theorization was also motivated by very practical concerns. If you get to the age of 45, you're lucky, perhaps. Childbirth, death in childbirth rates are astonishing compared to today. Welfare systems are so much different from what we have nowadays. If you get malaria, what happens to you? You die. In that sense, where does one look for comfort in life? One looks to philosophy, one looks to religion, to the black arts, etc. And scientifically, one might ask, if I could explain phenomena around me, if I can find a sense of ease with the physical world, I will actually change my relationship to the world, so that when the next earthquake does strike, as they did and do in the Mediterranean area, to understand seismology is to help to understand how to go through daily life. In this respect, I'd just like to inject the thought that for the ancients, the motivation for inquiry is not just, as it were, as an end in itself. And I don't doubt for a moment, of course, the practical applications of the science that you do. But for the ancients, there is an urgent ethical application of scientific inquiry, whereby I can come to grips with understanding my place in the world. Philosophies in which I am most interested, such as Stoicism and Epicureanism, literary responses to those are essentially preoccupied with, how can I live a happy life? And
I could be wrong about this, but my impression is actually that if you take the periods where science was making a huge step forward, or where thinkers about deep questions about many things actually seem to have made important contributions, was precisely in times where, for a period at least, they didn't have to worry quite as much about these kind of survival questions, where actually having a more a long-term view of history and life was actually often a more important motivation, and especially with the Greek philosophers, to me, they had an amazingly long-term point of view.
Forever and ever. But actually, Gareth, it is perfectly okay for you to doubt the practical application of the things that we do. So in that sense, I don't want to dissuade you from asking us.
Right. And actually,
is this of any value whatsoever? And so this is something that's actually very interesting. As we know, basic research, theoretical work, never changes the price of bread today. It could change the course of civilization tomorrow, however. Is that motivation enough for us, right? 100 years ago, when Einstein developed the general theory of relativity, it had zero practical value. Today, it's a multi-billion-dollar industry to put your Garmin and your TomTom on and to figure out exactly where you are within a few inches anywhere on the surface of the Earth. And without the general theory of relativity, that would be impossible, right? So actually, it's not a bad question to ask. So when we study, let's say the ancients were thinking about earthquakes. Poseidon, of course, was the earthquake meister, right? And so does that mean that to survive an earthquake, you pray to Poseidon? Was that the practical application of learning about earthquakes? What was the actual? Please tell us.
Well, I'm very it's actually I'm writing a book about Seneca, the good Roman Stoic. His writing on the natural world and his attempt to produce a consolatory form of rhetoric that will prepare you for the trauma of events such as we saw yesterday. Of course, it is fundamentally flawed. Anyone who's seen footage for a brief moment will realize that no amount of consolatory reassurance will, overcome the...
And reassurance of what? Exactly.
If you begin to understand that the events of yesterday, horrific as they were, are in fact entirely normative within the physical fabric of the universe, it reconciles one to the sense that, however shocking in the here and now, it is part of the overall process of nature. If on top of that you add a theological dimension, and for the Stoics, theology was actually a branch of physics, you then overcome obvious philosophical problems such as, if I am a good person, how can God inflict this upon me? And so in that sense, physical explanation of the universal workings is very much tied, obviously, to issues of great religious and philosophical
But
importance.
say more about this. It overcomes them how? Why doesn't it simply reinforce the horrific initial impression that the universe does things in a way that takes no account whatever of its consequences for me?
You're giving the universe too much credit, sir. Right? I mean, the universe is not doing anything on account of anybody in this case.
Right.
Right.
That's exactly.
And
but so
that's
why,
totally okay.
No.
Because
But what is consoling exactly? Isn't the thing we need to be consoled about precisely this impression that things are proceeding in a way that has
I'm
nothing
okay
to do
with
with
that.
my interest?
If you believe that the universal structure is essentially anthropocentric in its design,
Right.
an earthquake causes an instant big problem.
Right.
Exactly. If you're cool with the universe is just the way it is, and if you have a really crappy day, it's not that big a deal.
Yeah.
Right? There's some consolation in that.
Yeah.
Right?
Yeah, if something bad happens to you on a day, you're not going to. Even thinking about different universes, I would not say, "Why am I living in this universe, and why didn't I happen to live in this other one?" I deal with it in a much more practical way, and I actually have something in my mind which is fate or so, and I accept it. And there are actually colleagues that do talk about what they call the multiverse, that there are these other universes out there. I'm much more economical than that. And the fact, for example, that we cannot control our future destiny, again, for physicists, that can sometimes be a frustrating thing to think about, but I accept those things. But struggling with that, obviously, I think has been throughout history, something that made people have to choose between a rational explanation of what was happening and introducing things like deities or other forces that were given other names.
But maybe a question coming off of this is worth pursuing a little further. Look, if one is asked to say what it is about a particular scientific development or discovery that makes it deep or important or profound, if you're asked what it was that made the development of the heliocentric model of the solar system profound, or Newtonian mechanics profound, or relativity or quantum mechanics profound, or the discovery of the unconscious profound, or the theory of evolution profound. One answer you could give is that all of these were profound in virtue of somehow putting in play or at risk or under threat attitudes toward the world which are very close to the core of who we are, and of how we make our way through it. And all of these developments are important, at least in part, because certain elements of that were thrown into question. What's the right thing to say to someone who says distinctions between string theory and brain theory or loop quantum gravity or something like that are not of this order? They're very fundamental in some purely logical sense, in the sense that we hope that from them we're going to get all these other theories. But it's not an arena, or somebody might say, it's not an arena in which anything terribly important to the way we've always thought about ourselves is at risk.
That's a good question.
Well,
But
can I try to reframe that a little bit from my non-theoretical perspective? When we think about a theory of everything, normally I think back, and forgive me if I'm being too simplistic on this, to Einstein when he first formulated the general theory of relativity and considered time as a fourth dimension which was knit with the three dimensions of space to create this very strange mathematical manifold. The Einstein equations actually a series of many partial differential equations that can yield almost an infinite number of possible results. And what happened was, after he set that original framework, many people then went on and tried to find specific solutions or specific characteristics of the Einstein equations that actually reflected our reality as we saw it. In other words, from a many-faceted thing, we pull out one thing that reflects reality, hence things like the Friedmann equation, for example. Now, this is a very simplistic way of imagining. If we thought 100 years ago that general relativity was a theory of everything, and then we pulled out one strand that reflected our own reality. Today, if we think of string theory as a theory that can encompass a myriad number of possibilities, and we're trying to pull out the one thing that actually reflects reality correctly, then I would submit that all of these ideas of what might be truly string theory are indeed potentially fundamental, because we're trying to find the actual description of reality that way. Herman, for example, I won't, I read a paper that he wrote a few months ago. It's very complicated. But again, you have multiple dimensions, 7 brains, D3, things like that. You take this thing, and he was trying to pull out individual solutions. If you do this, then you actually get back this kind of theory. You perturb this one. So this is one possible set of solutions from this very, very complicated structure that allows it to happen. Glenys, in her work, for example, she was just telling me, and I knew this also, but she's doing computational simulations of a pair of clusters of galaxies that are colliding and possibly can give us a great deal of information about dark matter. And what she's doing is she's taken, with her colleagues, a whole bunch of pretend particles of matter and gas and dark matter and fluid and so forth, and then dropping them into a computer and letting the computer run. So again, from a myriad of possibilities, one result is coming out. She's going to get one thing that may or may not reflect reality. So is it noble and meaningful to have many, many possibilities narrowed down to one? And that one is the theory of everything. I'm cool with that.
I'm not sure I understand. Let's see. This is less true of F equals ma than of general relativity. F equals ma has an infinite number of solutions, too.
Well, no.
What we pull out one which resembles the actual history of our world.
It is a little bit different. F equals ma is one equation, but the Einstein's equations allow for F equals mb, F equals mc,
Sure.
F equals md, F
Sure.
equals me.
Sure.
So the fact that...
But F equals ma allows for worlds radically different from ours, in which there's a single particle, in which there's nothing, in which all there is a huge scale model of Bozo the clown, all sorts of things.
But just because it can explain other universes doesn't necessarily explain ours. And it turns out that Newton's equation is flawed in explaining ours.
Sure. No.
So
I'm
that's
trying
my
to
feeling
understand.
of what...
I'm trying to understand what you meant by pointing to its allowing for an infinite number of possibilities.
But yeah, I understood your question a little bit different, which I thought was rather a good point. Should we expect to get insights still that will really alter our worldview
Right.
at a more fundamental level, and again make us seem less special? Because usually that's
or
typically
something. Something deep is going to be at risk.
Yes, there are certainly there are deep things at risk right now. And again, someone in the end of the 19th century could have still asked the same question, where they were also thinking, okay, well, we basically know the laws of physics. Do we have anything left to discover?
Sure.
And
Indeed, they did.
They did. And of course, quantum mechanics came, etc.
Right.
And do we have similar big puzzles at the moment that should that we already know will have to drastically alter
Right.
our view of how the
Right.
world actually fits together. And yes, we do. And we talked about the cosmology, the fact that the world, why is the universe so big?
Right.
I remember being, when I was growing up, I thought that, okay, well, the universe could be infinite. Okay, imagine it's infinite. Scary thought, and I didn't accept it because if you keep going, it's too scary to think that it's infinite. But imagine now it's finite. So, okay, well, you come to a wall, and there it stops. Okay, well, what's behind it? And I could be awake at night thinking about one of the two options, and I couldn't accept it. So I actually thought it was actually very reassuring, at least that Einstein's equation was mentioned, gives the possibility of having something that essentially you think about the universe as a sphere.
Finite but unbound.
Finite but unbound.
Right.
And I thought, hey, yeah, I can sleep again. So fine, thanks to Mr. Einstein.
Right.
But then you learn more about quantum mechanics, etc., and then it turns out that we actually cannot explain. We have essentially we pretend that we have something that looks close to a theory of the universe, but we have this calculation in our back pocket that basically predicts how big our universe should be, and the size is roughly this, which is the problem of the cosmological constant, because basically our universe should be filled up with stuff. Stuff has energy, and Einstein says energy is mass, and he also said mass curves the universe. And we're in a big conundrum there, and so there's certainly a deep insight still waiting for us somewhere, which may have deep implications of how we view, maybe not everyday applications. It may not have a consequence for how we're going to manufacture a new computer chip or something.
No, but let's separate practical. I think one can separate things like technological spin-offs. No doubt Newtonian mechanics had tons of technological spin-offs, but it had an effect of a completely different kind. The Enlightenment, the rise of liberal democracy, so on and so forth. That is completely independent of its technological spin-offs. It was clear that it was putting in play very deep features of how we think about ourselves. And one can say, I think, in a similar vein, that that relativity and quantum mechanics had a lot to do with the zeitgeist of which literary modernism was a part, and so on and so forth. There was another sense in which deep commitments of ours, not in the technological sense, but deep commitments about how we describe ourselves to ourselves and how we describe features of the world that are important to our lives to ourselves were in play there. I can imagine someone saying, I don't know if this is something I agree with, but I can imagine someone saying, I don't see the same stakes here. That is, once we've got 4 dimensions instead of 3, the jump to 11 is not such a big deal. Okay? Or 27 or something like that. Now, I don't know. What does one think about this?
Extra dimensions certainly would be a big deal. I wouldn't necessarily imagine that we would convince ourselves that we can enter those. But there are many things still about that can change our worldview. And presently, I think one of the things that has been changing has had a deeper impact. Things like the Hubble telescope. Simply the fact that you can now see pictures so far away. And it's almost as if you can touch these things that are so far away. Certainly has changed our worldview.
Or colliders too, don't they? Don't they? The Hadron Collider.
The Hadron Collider, yeah. So a couple of months ago, I gave a talk about. I was I used to give a talk about black holes. And of course, the thing that struck me so much, we all know the story that when the rumor was there that perhaps because of the extra dimensions that the collider could make black holes, I don't think I met any person anywhere that hadn't heard that story and immediately had a reaction to it. So this whole idea that there might be the possibility of creating a black hole right here on Earth, it made clear that the notion of a black hole was something that was actually a pretty primal fear, much bigger than the actual physical object deserves. But in that respect, black holes are an example of something that actually sits in our worldview. Because nowadays if money disappears, which has happened here, not too far from here, there's probably a black hole here in Manhattan somewhere for sure.
But David, don't you think that if we realized that we were made of 11-dimensional particles, it would change our worldview as much as when we realized we were 4-dimensional, as much as it realized when things are not micro-deterministic?
Well, spin that out a bit.
Okay.
Speculate about what the effect would be.
I am struck. I'm reminded now of somebody who came to me a few years ago at the Hayden Planetarium and said, "I'd like to talk to you about my idea of the universe." I was like, okay. And he spent about an hour explaining to me the possibility that there are many more dimensions in the universe, and that string theory is just talking about space as 3 dimensions of space and 1 dimension of time, and then the other 7 dimensions are things like love, loyalty, faith, that kind of thing, right? So,
but
wow, wouldn't that be cool?
Wait,
I'm sorry, I've used cool like 3 times this month.
Is that the kind of effect it's going to have?
We can only imagine. But yes, suddenly the human condition becomes far more in-depth, far greater and richer than it could have been before.
I don't know how seriously this was intended, but let's pursue it a little bit. If somebody says one of the other dimensions is love, I simply don't know what that means.
Right. Well, in the 1800s, I believe there were natural philosophy papers written about magnetism. Right. The reason lodestones connected with one another is because they love each other. But of course, if you turn them around, they'll repel because they hate each other. Love and hate are the same sides, 2 sides of the same coin, right? We laugh today, but my freshman physics professor said he actually showed us this paper at the beginning of the semester, and at the end of the semester he said, "You see, this physics stuff is pretty counterintuitive. It's very strange. The idea of electrons floating around, the idea of magnetic fields, electric fields, whatever. But just as we today chuckle at how those natural philosophers tried to explain magnetism with love, perhaps we are getting closer to actually understanding those lodestones as things actually existing in the universe, maybe a Kantian thing in itself or something like that. And so we allow the possibility that we are getting closer to the thinginess of ourselves in the universe if we see that indeed we are more than 4-dimensional creatures. Am I getting too crazy here?
No. Maybe.
I think it's fair to say that it's good to remind ourselves, too, though, that without puttering around with the theory of everything or the underlying fundamental theory, there's certainly scientific discoveries that will have even a more great impact on ourselves, like discovering how life originated.
Oh, sure.
And discovering other examples of life and things like that.
Oh, sure. No, I was trying to focus on what I took to be the focus of the panel today, which are these fundamental physical theories. I mean, maybe it's worth, and are we supposed to wrap up pretty soon? Maybe it's worth, you brought this up, maybe it's worth composing a list of what look like fundamental problems in physics and the impact that we expect things like string theory or quantum loop gravity or something like that to have on them. So maybe I'll start out as moderator proposing one just so that people can have something convenient to shoot at. I take it there are three really fundamental, outstanding, unsolved problems at the foundations of physics. One is what you might call the problem of the elementary physical constituents of the world and of their dynamics. That is, the business of, say, unifying general relativity and quantum mechanics comes under this heading, so on and so forth. What we want here is to write what would constitute solving that problem is to write down the correct Lagrangian or Hamiltonian or some analog of one of those of the world, and saying, here's what the fundamental constituents of the world are. Here's what the fundamental particles or fields or strings are. Here, moreover, is the dynamical law that governs their evolution. Good. That's one problem. Second problem, which has been sitting in physics for a long time and has a complicated relationship to the question of dynamics, is the problem of the direction of time. Okay. For people who aren't familiar with this, it's been a common feature of every fundamental dynamical law that anybody in physics has taken seriously since the Renaissance. And this is quite a striking thing, because the kind of dynamical laws that we've taken seriously since the Renaissance have undergone very profound changes. Changes we've talked about here in whether they're deterministic or not, changes in the structure of space and time, so on and so forth. Strikingly, through all this, every serious proposal for a fundamental dynamical theory of the world shares the feature that there's a deep sense in which it doesn't make a distinction between past and future. Okay? That is, it shares the feature that for any process that it allows the same process to happen exactly in reverse. Okay? And for a number of reasons, it couldn't be more obvious that this claim is belied every second of every day by the most common experiences of our life making our way around in the world. First of all, the world is swarming with processes that only happen in one direction: the spreading of smoke, the cooling of soup, the aging of people, so on and so forth. On a second level, we have a profoundly different epistemic relationship to the future than we do to the past. That is, the kinds of things we can know about the future and the ways we get to know about the future are radically different from the kinds of things we can know about the past and the ways we get to know about the past. And third, we walk around with a very deep conviction, which is very puzzling in light of this mathematical feature of the dynamics, that something, I don't know how to exactly sum up this conviction, something along the lines of, by acting now we can affect the future but not the past. All these things are very mysterious when put beside this perfect time symmetry of the fundamental equations of motion. So that's the problem of direction of time, and I won't go into as much detail about the third one, but there is a puzzle at the foundations of quantum mechanics called the measurement problem. If I had to pick the sort of large unsolved problems that are confronting foundations of physics now, I guess that would be my list. And maybe here's a question. Usually what we mean by theories of everything, string theory, brane theory, loop quantum gravity, blah, 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 all of these are aimed at solving problem number one. And most of them don't even pretend to have much to say about problems 2 and 3. Is that because problems 2 and 3 aren't real problems, or is something else going on? And I assume this is the case, do people want to pose different lists of fundamental problems? I leave it to you.
I'm sure both of us want to comment.
Okay.
I don't think 2 and 3 are problems. They are understood, and it's the question of interpretation of measurement and things. It's what picture you want to attach to the mathematics but that's sort of your own private business. Do you need to attach a picture? So I don't think it's mandatory that you have to attach a picture. And the direction of time, I think, is very well understood. It's like the problem of it's easier to get out of a parking place than to get into it. There's more ways to go forward than there is to go backwards.
That applies in both directions.
That's right.
You take the macro state
that's
of the
right.
world
And
now.
I'm sure you know this, so I don't know quite why you're bringing this up. I mean, it's just not an issue because if you ask how many ordered directions are there compared to unordered things, and there's just a lot more ways to be unordered, and it's just that simple. And
well, okay, I guess I disagree about the last two problems, but I don't want to.
I mean, why? Another way to put it, though, that is puzzling is why is it that the universe is evolving in such a way that there was this? Well, you could say that we're expanding, and in some sense, right. So asking about the initial conditions is maybe a physicist's way of paraphrasing that. But that's certainly a
well, look, I don't want to hijack this too much. I mean, I just the characterization. Yeah, I think you're making a mistake about the measurement problem, and we could, but I don't want to hijack this too much on these two.
Yeah,
okay, you had something to say.
Yeah, I think I'm maybe a little bit in the middle between the two of you. I agree with Glennis that the last two problems are of a very different nature than the first one, and that indeed to a large extent we kind of know the answer to the second two. But both with time and with the measurement problem, I do also agree that at a more philosophical level that there are things, sort of left open, and the measurement problem more has to do with the discrepancy between what we can do in physics and what we experience. The fact that in physics we can predict one of again many possible outcomes, and we only have one experience. So this whole idea that there might be many worlds out there, and that every time there's a decision.
Well, the trouble isn't that there are many possible outcomes. The trouble is that what the equations of motion predict is a coherent superposition.
Whereas our experience only picks one of those.
Right.
So yeah. Okay, fine.
And look, the attempts to approach the measurement problem that look to me to have any chance of being satisfactory aren't matters of reinterpreting the formalism. They're matters of actually, say, adding nonlinear terms to the Schrodinger equation, adding extra variables to the physics we're describing, so on and so forth. So I don't think it's an interpretive issue.
Although I would call it, I think we sort of practical physicists would call it maybe an overreach of what theory should do. I made that concession. At least most of us may have made that concession a long time ago, and we don't want to sort of come back to it in some ways.
I just have a simple question to ask. It seems to me when I went to school, physics was very simple. And now physics is so complicated, it's very hard to understand. But it's not what school, it's a long time ago. So now physics is, I mean, when you guys talked about multiverses and so on and so forth, it's significantly more complicated than it was, let's say, 40 years ago in terms of what's happening. And I think there was, you mentioned something about that, alluded to it indirectly. What is it that is pushing us into not just being satisfied with the easier, simple things we had and keep complicating and going into more and more? What's this? Where does this need for searching and discovery and more inevitably becoming more and more complex coming from?
The world.
Yeah, but why does the world?
Maybe I could say.
The ancients is what you were saying.
Well, that's what I'm trying to.
Well, just to give a quick classical response. One of the reasons I adore studying the ancient world is this. It is the restlessness of energy and inquiry. It's not just in terms of scientific thought, but in terms of ethics and in terms of literature as well. The ancients, someone like Lucretius or someone like Seneca, tries to find a physical explanation for something, and that gets so far, but then a balance of the probabilities means that a side issue needs to be dealt with, and so the debate goes in that direction. What I am so impressed by the ancients, and of course you could do this in the modern scientific age, I'm sure, obviously, is the sheer restlessness of inquiry, of the thirst to see a problem.
But that's not an answer, that's
no,
an observation.
But through looking for problems, it creates a mindset and appetite, which I would suggest does become an answer. It creates a critical ideology, a restlessness with complacent acceptance of answers, and perhaps one of the reasons why ancient Greek and Roman culture is extraordinary in the arts as well as technology is a certain restlessness for inquiry. And if I may add a second point, of great interest to me is science as rhetoric. The extent to which, for the ancients, when there is not empirical proof, it is argument. How convincing can I make my proposed explanation of X phenomenon? Mm-hmm. Now, I assume that for modern scientific investigators, rhetoric is out the window.
Oh, no.
And yet,
No.
I would hope, in a way, and my little toe going into the waters, I've been very interested recently in the rhetoric of science movement, the extent to which certain individuals are very fascinated by, the extent to which you can create a rhetoric of non-rhetoric. For the ancients, this is very interesting. The extent to which scientific reflection and theorizing is as much an exercise in rhetorical persuasion as it is in the basic science. That's all I think.
But I think you take for granted the existence of consciousness in your explanation. But if you say there, at some point there is consciousness, and then because of that consciousness, then we want to learn more and more and more, you still are left with the problem of why, when there is consciousness, there is this need to learn more and more and more.
The way you put that at the end makes me think I maybe misunderstood the previous version of the question. But if you just ask the question, why does physics seem so much more complicated now, and dealing with all these, in a way, there are all these, we would call them scenarios, all these different ways things might be, and they have...
No, I didn't mean that.
Oh, okay.
No.
But
I
I was
understand
gonna
why
offer an
physics
answer
is
to that.
getting more complicated.
Oh, okay, great. I had an explanation for
What I don't understand is what is the drive that leads us towards finding more and more complicated things in nature, rather than just saying, okay, we have enough, we know enough, the world is round, and that's it, forget the back.
Well, you know what, I do want to inject something which probably we should have mentioned. I think there's actually a deeper reason that fundamental physics has gotten complicated. It's that in this period when people were just trying to understand what the laws were, kept busy at it and do a pretty good job, and the laws that we knew of when you were studying physics were a smaller number, actually. But then there's the thing that was a huge transformation in the last 30 years, I guess I would try to count. Time goes by. Maybe it's more than that. No, yeah, it's more than that. But anyway, basically, with these well-understood laws, the thing that was so paradoxical, it's as if they just didn't go together properly, because gravity is just such a different nature, and it has this, you can think of it as a Planck scale, a mass scale, or a length scale, a length scale that's incredibly tiny, or a mass scale that's huge, compared to the ones that are associated with all the rest of the forces. And when you sort of think, when you try to apply the physics that you think you understand, it makes no sense at all that they would have such different properties, that they, just because of all, they have common interactions, they would sort of all get to be more alike. It's a kind of common experience, and it's the same in the physics equations. And so I think that's really driven a real. I'm old enough. I really feel like I see a change of character in people's in physicists' expectation of what amounts to a satisfactory explanation because of this thing. It's called the naturalness problem or the hierarchy problem. It's just like there's just two totally separate regimes that ought to kind of come together, but they don't. And so it just seems like something's missing, and that's, I think.
I kind of sympathize with the question also. You mentioned my paper, last paper, and if you would have not read try to read the mathematics equations, but try to extract the gist of the point of the paper, it's actually precisely sort of trying to push back on this, making things more complicated.
Yes.
And part of the whole point is that I've been advocating is precisely, okay, well, let's take the things that we know, and those are going to be our starting point, rather than initially trying to, because, okay, things may get more complicated if you declare ignorance about everything, and then you say, well, let's try to explain why things are here. But if you start from what we know that describes our world, then all these complications that people have, where there are too many possibilities, does get shrunk down to a much smaller set. So I've been often advocating a more practical approach where indeed precisely the simplicity should be brought back into it, because that's an organizing principle. You have to give yourself, when you look at a messy room, you have to give yourself an organizing principle. And I think science in that respect always goes through these periods of expansion where we're confused, things seem more complicated, and things will simplify once we find the new organizing principle.
Excellent.
If anyone would like to come up, just come up and then announce who you are, though. Show who you are.
Sure, I promise. I promise to try. Stuart Dambrot. We had a brief email exchange. So firstly, just a very quick observation about what drives human beings to this. Hilbert had a great saying: "We must know, we will know." All right, but what is the neocortical activity under that gives rise to that drive? And for me, it's just it kind of pops out of how our neocortex evolved to seek patterns, to impute meaning, to impute causality, in order to better negotiate our existence with an environment. So that's just my quick answer for that. But about so I have two things that I really would love comments on. You can yell at me about what I just said also. Firstly, it was mentioned a few times about complexity, emergence, and so on. But I'd like to know anyone's thoughts on the fact that when talking deterministically, the little we know of the early mathematics of complexity is that on the far side of a chaotic boundary, there are emergent properties that are not predictable, knowing the constituents on the closer side of that boundary. So some of these emergent properties, if these mathematical treatments turn out to be accurate and generalizable, would account for some non-deterministic properties at the quantum level and perhaps others as well. So some comments on that if anyone wants to. And then one specific question having to do with simplicity and organizing principles and Ed Witten. In 2003, Ed Witten wrote a 97-page paper integrating string theory and Penrosian twistor theory. And in doing so, even though Witten acknowledged that it is limited, a lot of interesting things happened. For example, Feynman's quantum indeterminacy and possible time reversal and non-causality disappeared. All of a sudden, there was determinacy at the quantum level through this integration, in that it's just that where and when things happened became a little more loosely defined. All right, so that's one thing I would love for Linda to comment on. And secondly, the good news is that it, without going into the details, it kind of addressed some of the shortcomings of string theory, while simultaneously reducing the number of dimensions required to explain some of these theoretical concerns. And as a bonus, space, time, and some other fundamental properties popped out of the integration. So any comments on that I would love.
I think you have asked me that.
Yeah, no, that's it. Thanks. I'm done.
Thank you. Anybody wants to tackle?
That was directed specifically to Herman.
Yeah. So the last one. So it's sort of coincident that in the last few months I've actually revisited that paper that you mentioned. I'll just mention a few things about it. So in the paper that Witten wrote back then, he was essentially trying to make organize the structure of a theory that looks like the theory that describes elementary particles, the quarks, so what we call a gauge theory. And he was not, at the time, he was not interested in describing gravity. But that paper actually, although it started out in development that's still going on these days, Witten actually considered it kind of a failure because he found gravity in his construction. And he wanted to get rid of it. Whereas actually, what I'm trying to do is to take that same idea and use the gravity to good use, put gravity to good use. So I think indeed it seems like that paper is sort of like a different starting point. And let me add this also. String theory, by the way, here it is. String theory is not a theory of strings. In string theory, string theory doesn't start by saying, "Hey, we're going to assume that particles are made out of strings." And at the moment, the best starting point for what I would define sort of what string theory is to take the same mathematical principles that we already know are successful in describing elementary particles, and use those tools to incorporate indeed gravity. And that actually at the moment is our best definition of what string theory is. So it doesn't start with strings. It makes use of the mathematical tools that we already know are successful in describing particle physics. So in that respect, I think the history has given sort of a perspective on what string theorists are trying to do, which I think is misguided at this point. String theory actually turns out to be a way more conservative starting point. So there are definitely a lot of things to be learned there. Coming back also to what was brought up about time, there are going to be indeed new lessons to be learned about it. If you keep sort of probing these particular questions.
I'm Fritz Kenzel. I'm a psychiatrist and psychoanalyst. I'm working on a theory of unconscious development. Tsunami has been mentioned several times. Could all matter be waves? Could light be a wave? Could substance be a wave? Could gravity be a wave? Could these waves have evolved? Could what we see in the universe be the end result of some stages of evolution? So that what we see now is a whole hodgepodge of very primitive matter and then more developed matter. And finally, could the mind be the ultimate matter wave? Could the mind be the wave that is actually, so to speak, the king of the whole of the whole shebang? I just throw it out for.
The mind would not be the king of the whole shebang in that case. The mind would be the foam on the crests of the ocean of waves that form the ripples of the Dirac Sea in that environment. Sorry, I just had to. Poetic Seneca. It was Seneca.
The rhetoric of science.
Sing to me, muse.
Thank you all for your time. My name is Stuart Barron, Gadfly at Large. We don't have microdeterminism yet. Eventually, it would seem to me that we may get there. I think I'll lob an answer to this arrow of time question. We are experiencing the illusion of progression through time as a result of the fact that we are a cascading sequence of events from the microcosmic to what we experience as the macrocosmic. And then a question. Do we tend to think that antimatter moves backwards in time?
Particle physicists can answer this question.
It's a perfectly fine way to describe it. That's what Feynman showed. It's a as a mathematical description, you can make a consistent theory that way at the quantum level, but that you don't have to do it that way either. So it's not, you take this, I think that's an answer to your question.
Yes. So if that were the case, then might there be another universe on the other side of the Big Bang moving the other direction in time?
No. I couldn't resist.
Hi. You mean that?
Yes.
We can discuss it later.
My name is Joe Cadlick. I'm a resident citizen at large. I want to go back to worrisome things that worry the project at all, of finding a sort of unified theory of everything, which I would dumb down even further to kind of like the explanation of what's going on. I mean, at the time it's asked. And that is the problem of being included, as a thinker, as a person, as in the actual fabric of the question. There's no outside of the question. There's no place to get where one can actually prove that this isn't a charade, in a certain sense. So maybe that's more philosophical, but I think that it's very fair to ask how within the developing story, as part of the developing story, can you possibly hope to prove anything?
Can a goldfish prove the size and shape of its tank? If it can, then we can prove something about the universe. We may not be able to prove everything, but yes, we can try to explain something larger than ourselves, even if we're part of it. I don't see the problem.
I think that I do somehow. I mean, if you're actually part of what's going on.
Is the goldfish part of its bowl environment?
Is it gold? Yes.
Okay.
So is it going to be able to prove what's going on with it?
Maybe. Why not? At least it can start. Right?
Right.
I mean,
to give the chemical structure of water?
Yeah, why not? Yes, exactly.
I take your word for it.
That's right. I mean, the fish probably can't break up the hydrogen and oxygen, but if there were fish chemists, why not? No,
I think it's a question that will sit with you.
You have a Cartesian philosophy, sir, that you're expressing right now, which I completely understand.
That doesn't make sense. The
brains and vats idea, right? Descartes himself said, if we're all brains and vats, how can we prove we're not? Well, the answer is we can't, but so what? Let's figure out what the brains and the vats are anyway.
That's fine.
Yeah. Are we cool with that?
Yeah, that was fine.
All right.
Thank you.
Thanks.
Yeah, hi there. Jenny Subramanian, great talk. My question as a layman.
Who are you?
Student of life.
What was your name?
Janu, Janu. Yeah. I've studied some physics, but as a layman, I feel like the missing piece of the theory of everything is, I think a point that was brought up earlier, is the interaction between mind and matter. Or if we don't have a theory of the interaction between mind and matter, or a theory of mind, how can we really explain everything? I mean, I think that seems to be neglected.
Well, let's see. I take it the presumption is that whatever mind is, if you have a complete account of the laws that govern the motions of, say, material particles, okay, that account, given the initial conditions of the world, is going to predict either deterministically or probabilistically what, like we were saying, how my mouth is going to move, what air vibrations I'm going to generate, how I distribute ink on pieces of paper, so on and so forth. The question is going to be, what is it about my mental life that's been left out of such a description?
I mean, how we experience, what are we...
Well, everything I say about my experience, everything I report about my experience, every motion I make, every distribution of ink marks I put on a piece of paper, every sound I make, if it's been granted that all of that is taken care of by the physics, okay, then the question is going to be, what is it that you're worried has been left out?
Okay.
Thank you.
Well, look, if there's something still hanging and you want to approach any of the participants later, you're welcome. We'd like to move on with the questions.
Malcolm Arnold. I'm the founder of Ruby Newbie and Agile Activism. In physics, there is forces at play that cause collisions. And applying a theory of everything, looking for a unification theory, not in physics, but in how we interact as humans. And taking the philosophies as far as looking for a unification theory of everything and taking that into our interactions, not as physical particles, but as people, what would be the guidelines that you would have as far as trying to find a unification theory for humans, as far as in the organizing of that, so that you address world conflict on a macro level and conflict on a micro level? And I have an invitation, if anybody, this is a question for the audience as well, if you want to talk to me about that afterwards, please come talk to me. But our mission statement is that we provide a path to success where equitability, social justice, sustainability, diversity, and sustainability are embraced. And those are the values that I looked at. But we're a very new organization, and I'm trying to figure this out as a way of a unifying principle. And y'all have looked at this as far as trying to organize a theory of everything. And these organizing principles can then actually be applied to how we interact as humans. And I'd love to have your guidance.
Thank you.
I would just say look to economics.
Game theory is what I looked at trying to see where the incentives are and realigning the incentives with the needs, desires, and goals of all the players in the marketplace, and then creating new incentives that have never existed before.
Thank you.
My name is David Hecht. I studied cognitive science, and I'm actually going to the study of architecture.
What's that?
I'll tell you about it later. But I wanted to go back to that very broad question that was brought up in the middle, sort of about the practical value of studying theories of everything, and kind of pose the question of how do theories that attempt to explain the natural world trickle down or broaden out into metaphors of explanation. So throughout history, as we go through periods of scientific revolution or explanation, we keep reforming our metaphors. And from atomism to mechanisms to relativity and its influences. And I think, I'd just like to see what people think about the possibilities for our current types of abstraction to ultimately not just be effective on a technological, which I think is a very broad level anyway, but on a level of explanation and how it changes the way we attempt to describe broad processes. Thanks.
Well, I think we were saying we've certainly seen that happen in very dramatic ways in the earlier history of science. Like I say, you can make an argument that there's a pretty direct line from Galileo and Newton, through Hume and Locke and Hobbes to the rise of liberal democracy. Okay, there's a certain image of the way the world worked that fundamentally changed what we thought about ourselves and what we thought about how society should be governed and so on and so forth. And I think you can also make a pretty tight association between what happened in theoretical physics in the early part of the 20th century, relativity and quantum mechanics, with the zeitgeist that's there in all kinds of artistic modernism and so on and so forth. There's a lot to say about that. Certainly not in the first case. In the first case, it's all about politics. Yes. Yes, the line is harder to draw there. That's right. I don't know. The question I was trying to pose is, what can we imagine in a similar vein for something like string theory. And I posed the question because I don't know the answer.
You have a question?
Yeah, how would you...
Would you come to the...
Sorry. My name is Stephanie. How would you describe the relation of information and matter?
Very short, but succinct question. Information is for us a pretty important concept. In some ways, actually, information is often quantified more in terms of our ignorance, and then we call it entropy, essentially. And indeed, in physics, it's actually very important to know how much you don't know. In that respect, this quote by Rumsfeld is actually pretty good. That unknown unknowns are much more dangerous than known unknowns. So knowing how much you don't know sometimes is actually a pretty important piece of knowledge. And it was mentioned the arrow of time, and essentially the arrow of time has to do with the fact that we constantly lose knowledge because there's constantly more that we don't know. So I would actually say there must be an intimate connection between how things evolve and our notion of what information, how information evolves. Yes.
Just as a follow-up, are they quantified in the same way?
There are certain things where they are quantified in the same way, at least certain situations where they're quantified in the same way. One example, indeed, I mentioned the black hole. You can sort of throw stuff into a black hole and then it's gone forever in some ways. And what we discuss, at least what's known, it's called black holes of the laws of black hole thermodynamics. That when you throw something into the black hole, that the amount of information that you lose can be precisely quantified in terms of the geometric property of the black hole. So we do make very important use of it. Another reason for why information is very important is that in some ways, imagine that, okay, we talked maybe at the beginning about what would be a practical definition of a theory of everything. And a theory of everything could be that you would imagine building a computer. One of my favorite examples is actually the movie The Matrix. Suppose that you would want to build the Matrix and actually create this virtual reality that would really look indistinguishable from our physical world, and you would have to make this computer program in a way where all our experiences would, even with the physical experiments that we can do, be reproduced. And then one question you could ask is, okay, well, how big does this computer have to be? How many terabytes? How many terabytes does it need to have? And in some ways, right now, we basically have an answer. We suspect that we know the answer to this. We know how big the computer has to be that could mimic our world. And the surprising answer is actually that the computer, although on the one hand it needs to be enormously big, but it's smaller than one would have expected. It turns out that the amount of computer power that you need does not grow with the volume of the space that you want to describe, but it grows with the area that surrounds it. And that's a deep insight that we believe must be explained, and that's connected again with one of the things that we hope would bring us to a next stage of understanding what nature really is.
We have time for one more question? One last question.
My name is Justin. I'm a student. I have a question for you, actually, as your strength here. You said in different universes, the laws would be the same, the laws of hydrodynamics, the laws of, or they would be similar, but however, like things like the mass of an electron could be different. I don't understand how that works. Would it just be, I guess you could say qualitatively they would be the same, or would they be quantitatively different? Is it different constants?
When I talk about things like gravity, thermodynamics, and hydrodynamics, you actually don't put in many. Those things don't really depend on constants. one of the things you can do with a lot of constants, like, for example, the constant that's related to quantum mechanics, we theoretical physicists are lazy people, so we put all the constants that we all need all the time, we put them equal to 1. And at that point, things like hydrodynamics, gravity, and thermodynamics essentially have no parameters. And they should look the same in other theories. That's what we call universal principles. And indeed, those things don't depend on details. And that's what makes them, on the one hand, fascinating, but also deep. Yeah.
And so something, if in some very vastly future time, the evolution of our understanding of everything were to be such that one would describe economics and try to understand it, it would be in that kind of a way. Right. It would be a sort of statistical theory, like in the way evolution is in some sense a law of nature, and it's not specific to the mass of the electron or something. So there's this kind of distinction which doesn't disturb us. But just
the value of the dollar is 1, and it doesn't.
No.